This is a video on effective nuclear charge, and we will be working off of our note packet that looks like this. Basically, it's just a blank piece of paper. But the first topic is something called effective nuclear charge. Okay, so basically, we have to start by talking about that. In an atom, of course, you have your negative electrons and your positive protons. Those of course, reside in the nucleus. So there are a lot of atomic properties that depend upon how strongly those negative electrons are attracted to the positive nucleus. So it's kind of the very underlying idea here that we have negative electrons, a positive nucleus, and there's a strength of attraction between the two. And of course, that changes based on how many electrons and how many protons you have. So kind of the foundation of this discussion is something called Coulomb's law, which if you've had physics, you've probably discussed that. So for our purposes, we're only going to look at this from a qualitative perspective, meaning we're not going to take this equation and plug numbers into it or anything like that, but it's still useful for us to know. So Coulomb's law basically talks about the force of attraction between two particles, and so that's what F is the force of, and it could be attraction or it could be repulsion. So in this case, though, we're going to be talking about attraction and not so much repulsion. But of course, a repulsion would exist between two charges of the two particles of the same charge. And of course, attraction would be two particles of opposite charges. So this law works for both situations, but we're going to be talking about it from an attraction standpoint. So Coulomb's law says that the force of attraction between two particles is equal to some constant k, which we're really not concerned with at this point, times the magnitude of the two charges. So that's what Q1 and Q2 are. They are the magnitude of the charges. So remember that magnitude just means size. So we're talking, is it a +1 and -1 charge? Is it a +2 and -2 charge? Is it a +1 and -2 charge? So on and so forth. Okay, so Q is the magnitude of the charges, and D is the distance between the charges. And of course, like I said, K is a constant that we're really not going to be worried with. So basically, Coulomb's law says that the force of attraction depends on two things. It depends on the magnitude of the charge and on the distance. So that's kind of an important takeaway point. Let me write that. So attractive force depends on, and again, this could be true for repulsion. Okay, if we were talking about two of the same kind of charged particles, but for now we're talking about attraction. So the attractive force depends on, one, the magnitude of the charges, and two, the distance between them. Okay, so that's kind of an important point. We're gonna keep going with that idea after I clean off the board. All right, I'm going to put that formula back up here. For us to think about for a second. Okay, so let's think about this as an attractive force, and let's talk about what happens to the attractive force as we change the magnitude of the charges and as we change the distance between them. So if you think about this, we'll talk about one at a time. If we keep distance the same, and we're going to talk about changing the magnitude of the charges and talking about how that changes the force. So think about it. Let's say we make Q1 and Q2 bigger, okay, while keeping D the same. If Q1 and Q2 get bigger, then the force of attraction gets larger, okay, mathematically, so that makes sense. If Q1 and Q2 get smaller, the force of attraction gets smaller. So that's a directly proportional relationship, is that as the charge magnitude increases, the force of attraction also increases, or you could say the opposite. So that's kind of our first point. So as charge magnitude increases, force of attraction increases. And also we could say as charge magnitude decreases, the force of attraction decreases. I'm just going to write and vice versa. But if you want to write both, that's fine. Okay, so as charge magnitude increases, so does the force of attraction. Or as charge magnitude decreases, the force of attraction decreases. But then distance is different. Notice distance is in the denominator of your fraction, so it's an opposite relationship. Holding Q1 and Q2 constant, if I make D bigger, right, if D gets larger, the distance between the charges becomes bigger, then the force of attraction between them is going to decrease. And vice versa. If distance gets smaller, then the force of attraction is going to increase. So as I should say distance, I guess. As distance gets larger, force of attraction gets smaller. And then, of course, the opposite is true. So my first bullet point is more of a directly proportional relationship, or at least a proportional relationship. And my second point is definitely an inverse kind of relationship. Okay, but I think that makes sense if you think about it. If you think about two particles and how they're attracted to each other, and you push them closer together, well, of course that attraction gets larger. And if you bring them farther apart, of course that attraction gets smaller. So the second point, I think, common sense wise, it does make sense to us. Okay, so now we're going to get into this idea of effective nuclear charge. Okay, so what we have to think about is that most of the time we're not just talking about a hydrogen atom, with one proton and one electron. We're talking about these mini electron atoms where we not only have attractive forces happening between the electrons and the protons in the nucleus, but we also have repulsion forces happening between all of the electrons. Okay, so we're going to summarize that. Let's see. Electrons attracted to nucleus, but repelled by other electrons. So the question kind of is, well, how do we deal with that? If they're being attracted to the nucleus but also repelled by the other electrons, how do we go about factoring that into our discussion? So we kind of view this as like an average situation. We kind of merge the two together. So what we say is that, and this is kind of the big deal, that the valence electrons are attracted to the nucleus, but at the same time that they're being attracted from the nucleus, the word is shielded. That they are shielded by the other, or in this case, the core electrons. So if you think of a shield, okay, and what a shield does for, let's say, a soldier or a warrior or whatnot, a shield protects them. So that's kind of what's happening here, is that the inner electrons are kind of getting in the way. They're kind of protecting the outer electrons from the full force of the nucleus, which means that those outer electrons aren't experiencing the maximum attraction to the nucleus because those other electrons are getting in the way. And that idea in chemistry is called shielding. Okay, when the other electrons kind of get in the way and absorb some of the attractive force of the nucleus. So what we have to talk about is this idea of, well, then if the electron is not experiencing the full attraction of the nucleus, what kind of attraction is it experiencing? Okay, so if the electron's not experiencing the full nuclear attraction, what force is it experiencing? Or maybe how much of the maximum could it be experiencing, if that makes any sense at all? So there's a little formula that we're going to get into, and this idea is called effective nuclear charge. So this, about if it's not the full attractive force, what force is it? That force is called the effective nuclear